One of the funny things about this book is the problems don't reset every section. So we're in 3.7. We're on problem 260. And you know that there's a lot of problems because I have been making you do them. But it's also funny to see the big numbers. All right, 260. So a lot of these early ones are just rephrasings, different phrasings of the problems that we've been doing. This is literally the first problem in the homework assignment. Use the graph to sketch the graph of f inverse, and then use part A to estimate f inverse prime at 1. So let's copy this graph down real quick. So this is a line. And specifically, it's a line that goes through 0, negative 3, and 2, 1. And then it's a line so that has slope 2. And the line looks like this. This is our function f. So if it goes through the point 0, negative 3, that means the inverse function goes through the point negative 3, 0. Inverse functions are all about switching the x's and the y's. This is the point 2, 1. That means the inverse function goes through the point 1, 2. Red graph has slope of 2. Blue graph has slope of 1/2. Kind of like so. Kind of like so. All right. And so we've done part A, sketch a graph, and estimate the derivative of the inverse function. It looks kind of weird, but that just means derivative of the inverse function at an input of 1. So it's asking, what is the slope right here? Well, it's a line. The slope is the same everywhere, but specifically, the slope right there is 1/2. And the slope is 1/2 everywhere. So the derivative of the inverse function when x is equal to 1 is 1/2. We're specifically looking at this white point. That's how you approach these problems. Right, the other ones are going to be a little bit more involved. Right, this one, you're estimating it. But remember, you can just estimate the slope of a function somewhere by just drawing a tangent line and estimating the slope. Like you draw a tangent line and say, oh, okay, kind of looks like it goes through roughly this point and roughly this point. This slope is about 1/2. You make approximations, but that's kind of how you do it. All right. Oh, I don't have my lights on. I turned them off for student hours. Let's do number 264. And you can all meditate on 264 while I turn on my lights. Wait, I didn't show you where it was to meditate. All right, meditate right here. All right, great. Hopefully you already have all the answers. So our function is, let's not do 264, let's do 266. We already did enough lines. F of x equals 9 minus x squared. And x is between 0 and 3. Why does it matter that it told us that x is between 0 and 3? 9 minus x squared is the function that we're looking at. Why does it tell us, and why does it matter that we're only looking from 0 to 3? Because we're talking about inverse functions. If we didn't have a domain specified, this is not a one-to-one function. This does not have an inverse function. And that's why this requirement is important. It doesn't have to be 3. It could be 5. It could be infinity, whatever. But that's why they're doing this. Otherwise, there is no inverse function. Now this is one-to-one. Now it passes the horizontal line test. Okay, find df dx at x equals a now. So we find the derivative. by first finding the derivative function, which is just negative 2x, and then evaluating it at x equals a, negative 4. Again, a here is 2. For b, find x equals f inverse of y. What is the inverse function here? Okay. So again, to find the inverse, you switch your x's and your y's. The wording is a little confusing, but this is what it wants you to do. Then again, that's going to be y squared is equal to 9 minus x, or y equals the square root plus or minus of 9 minus x is normally how we'd approach this problem. But this is not a function. It has a plus or minus. So we have to decide, are we using the plus component or the minus component? And that's another place where this comes into play. We're looking at the positive component here. Because, look at our graph. The y is equal to the positive version. We're dealing with all positives right here. This gets much easier with this domain restriction. This is our inverse function. So we're going to fully answer this question by saying the inverse function is the square root of 9 minus x. And our domain of our inverse function is the range of our original function. What's the range of our original function? The y values here? The y values go from 0 to 9. So here the x values of our inverse function go from 0 to 9. Domain of a function is the range of its inverse, and vice versa. X's become y's, y's become x's. All right, and then part C. Using part B, find the inverse function at y equals f of a. Also, actually, it wanted you to write this as a function of y. Technically, I would take this as an answer. But really what it wanted you to do was to call this variable y. It doesn't matter what we name our variables in general. But if we name our variable here y instead of x, x is normal. But if we name it y, then this y really is the same as this y. Right? Y equals this function value. It's the same y. So this is what we want to do if we want to be precise. All right, find the derivative of the inverse function with respect to its variable, and its independent variable is y, evaluated at f of a. All right, there's a couple of ways of doing this. All right, you could just take the derivative of this inverse function. You could use the inverse function theorem. I actually don't know what the book wants. It wants you to use part B. Yeah, it wants you to just take the derivative with respect to y of our inverse function, square root of 9 minus y. Write that as an exponent of 1/2, and then evaluate it when y equals f of a. What is f of a? Let's nip that in the bud. A is 2. So f of a is 9 minus 4. So f of a is 5. So we're going to take the derivative, and then again, we haven't used this notation very much, this Leibniz notation, so this is good practice and good review on that. Take the derivative, and then we evaluate with that. That's what that means. So, chain rule. Bring down the exponent. Leave the inside the same. Subtract 1 from the exponent. 1/2 minus 1 is -1/2. Multiply by the derivative of the inside function. What's the derivative of this inside function? Derivative of 9 is 0. Derivative of minus y with respect to y is -1. And again, once we're all done, we'll evaluate when y equals 5. That's going to be 1/2 times 9 minus 5 to the negative 1/2 times negative 1. And continue simplifying. Negative 1/2 times, this becomes 4. Negative 1/2 exponent means that 4 is inside a square root in the denominator. You're going to get negative 1/2 times positive 1/2, or negative 1/4. And the inverse function theorem should also give us the same result. So this is all the book wants you to do for this problem, but it would be a good idea to also use the inverse function theorem. The derivative of an inverse function, let's actually use the same notation. F inverse prime of x is 1 divided by f prime of f inverse of x. Well, f of x, remember, was, I don't remember, 9 minus x squared. So f prime of x is negative 2x. And we're looking at, we're looking specifically at a here, which is 2. What is f inverse of 2? That is, in other words, f inverse of 2 is for what x gives y equals 2. Wait, hold on. Did I get it backwards? F inverse of 2, f inverse takes in a y value and spits out an x value. Oh, it's because we're not looking for this. That's why it's wrong. I tried to. We're not actually looking for f inverse of 2. Right, what is it actually asking us to do? At y equals f of a. So it wants us to evaluate this at f of 2. It wants us to evaluate this at f of 2 is 5. If we were using the inverse function theorem, it would look like this. 5 equals 9 minus x squared. F inverse of 5 is 2 because f of 2 is 5. These are related concepts. So finally, f prime of f inverse of 5, well, that's f prime at 2. What's f prime at 2? Negative 4. So 1 over f prime of 2, 1 over negative 4. It's another way of using it. You don't have to do anything on this page. This is just a way to connect the concepts. I'm saying that phrase so much today in student hours too. And just check another way to check our work too. All right, 290. Find f inverse prime at a. Or f of x equals, oh, it doesn't tell us. F of 6 is 2. F prime of 6 is a third. And a equals 2. We're just going to use the inverse function theorem again. That says that f inverse prime at a, which is 2, is 1 over f prime of f inverse of a, which is 2. Start from the inside, work your way out. What's f inverse of 2? F inverse of 2 is 6 because f of 6 equals 2. That's the definition of an inverse function. The inside becomes the outside becomes the inside. So this just becomes 6. What's f prime of 6? It's a third. What's the reciprocal of a third? 3. You could also get this by multiplying by the LCD. 3 over 3. The top becomes 3, the bottom becomes 1. Another way of getting to the right answer. So sometimes when I'm recording these selected homework problems, I feel like you can just hear when I'm tired and hear when I have a lot of energy. Let's do 296 instead. A building that is 225 feet tall casts a shadow of varying lengths as the day goes on. I'm going to draw my picture, copy it down. This is 225 feet. This is X. This is theta. Right? So this, this is our little building right here. This is an example of when the sun is right here. I'm not going to draw the sun. That's too many strokes. And then as the day goes on, the sun is here and then there's like no shadow. So like, it depends. Small shadow right here. Big shadow early in the day and late in the day, so on. Find the rate of change at the angle of elevation d theta dx when x is 272. Find d theta dx evaluated when x is 272. Another way of phrasing this with Leibniz notation. Leibniz notation is the dy dx, d theta dy, d whatever. All right, as opposed to like f prime of 2. That's Newton's notation. Okay, so let's find this. So to find the derivative, we need the original thing. Once we have the original thing, theta, once we have theta in terms of x, we can take the derivative. So what's the relationship between theta and x? How do we relate theta and x? We're also going to relate 225 with trig. That's tangent. The tangent of theta equals opposite over adjacent. Excuse me. So this still is not a function of theta. Later on, we'll talk about something called implicit differentiation, which makes this next step actually a lot nicer. But we're not going to do that here. Here, we're going to solve for theta. Once we can solve for theta, we can take the derivative. Well, theta is going to be the arctan. You can take the arctan of both sides. Or inverse tangent. I'm going to try to be consistent. I love arctan instead of inverse tangent for a variety of reasons, but we're writing down inverse tangent basically everywhere in this section. Now, as long as, actually for sine and cosine, you really have to worry about restricting your domains. But here, inverse tangent's actually a pretty nice function. Because tangent, right, tangent looks like this. Inverse tangent is what happens when you flip it on its side. Inverse tangent actually has a domain of all real numbers. It's just the range that doesn't repeat, because tangent repeats, but inverse tangent doesn't repeat. Okay, so our theta is going to be in that range anyway, right? Theta is an acute angle, so these are going to be the same. We don't have to worry about any special domain things here because theta is acute. So again, normally these are not the same. Normally they're related, but they're not the same because it has to take into account domain and range if you remember from your trigonometry. But here they are the same because theta is acute in their interval from 0 to pi over 2. It's in that open interval. It's not going to be either one of those. Well, now we can find the derivative with respect to x. That's going to be the chain rule. Derivative of inverse tangent. Oh, I'm doing it again. Is 1 over 1 plus x squared. You can't escape the arctans. I love my arcs. I really do love my arcs because in League of Legends, there are arc-like skins that I also like. Anyway, inverse tangent is 1 over, the derivative of inverse tangent is 1 over 1 plus the thing squared. but we need the chain rule. So that thing needs to stay the same. 225 over x. Oh, this is kind of similar to a problem we did in the last video. We need to multiply by the derivative of that inside. Well, what's the derivative of that inside? That's the same as the derivative of 225 x to the negative 1. Very similar to that earlier problem we did. So that's, again, negative 225 over x squared. You could take a couple steps of getting there, but I'm just going to do the shorter steps since we've done quite a few problems like that right now. All right. This is our derivative. Let's simplify. Negative 225 over, distribute that x squared. That's going to be x squared plus 225 squared. What's 225 squared? I don't know. 5625. And then we're multiplying by an x squared and dividing by an x squared, so that part's going to cancel. This is the derivative of the angle with respect to x. And specifically, it wanted us to look at it when x was 272. Just plug in. The d theta dx evaluated when x is 272 is negative 225 over 272 squared plus 50,625. Whatever that is. It looks kind of messy. I already forgot it. Negative 225 divided by 272 squared. I'm forgetting it so quickly. Plus 50,625. All right, not very quickly. 0.001806. What are our units here? It's a derivative. Derivative is a rate. The units are going to be the units of theta divided by the units of x. Units of theta, it didn't really specify, but it's radians. Units of x is feet. So what this means, hold on, it's going to be a little easier to interpret this if we convert it to degrees per foot. So we have radians, right? And we know that pi radians is 180 degrees. So we want to multiply by this. The radians on the top, radians on the bottom are going to cancel. So multiply by 180 over pi. That'll be about 0.1035. Degrees every foot. So at this specific moment in time, this is about 1/10 of a degree every foot. At this specific moment in time, let's use their picture. And I'm going to say this sentence again. At this specific moment in time, in the day, how fast is this angle changing? For every foot, the shadow gets longer. The angle decreases. It decreases. It decreases. So there's a typo here, right? I lost my negative. But again, as this angle is getting bigger, or as this shadow is getting bigger, this angle has to be getting smaller. So that's why I knew the derivative had to be negative. As for every foot that this angle increases, at every foot that the shadow increases, angle gets about 0.1 degrees smaller. And that's only at this moment in time. That's the slope, the rate of change at this moment in time. But eventually, right? Eventually, the shadow is getting way, way, way longer. And the angle is not changing that much. You know, when it gets like really late in the day or early in the day, depending on which way is north. Okay. That's kind of connecting all the dots here. Okay. That's it. I would take your answer in either form. I think, yeah. This is what the book wanted, probably. I would take either. As long as you know and you're very clear about what units you're using. But basically always, unless it's specified in degrees, we're going to be using radians and calculus. Let me know if you have any questions, and good luck on the homework.